If you are a radio amateur, you will face the problem of calculating pulse transformers. Now, of course, there are many computer programs that will make a difficult calculation for you. We want to recommend our mobile applications for calculating pulse transformers of push, pull, and single-ended power supplies. Applications are highly accurate and very convenient. In the database, you will find a huge number of different magnetic cores. Application for the calculation of push-pull converters allows you to very accurately calculate the parameters of the transformer for push-pull circuits, bridge, and half-bridge power sources. The second application can do the transformer calculation for a single-ended flyback converter. All links are in the description. Hi friends, today we will again talk about impulse units, or rather about a simple but very good current and voltage stabilizer. The video will be long but very interesting, of course, for interested people. So sit comfortably and let's start. Such a stabilizer has a very high efficiency due to the pulse principle of operation. The output current can be up to 15 amperes, which will allow to build powerful chargers and powerful supplies with adjustable current and voltage. It is important to note that this is namely an adjustable current and voltage regulator. Through the use of field effect transistors, it was possible to greatly increase the load capacity of the unit and reduce the heating on the power elements. With an output current up to 3 to 4 amperes, the transistors and the power diode practically don't need radiators. I also want to note that the nominal values of some components on the diagram may differ from the values on the board, since the board was developed for my own needs. Let's examine the main technical characteristics of the stabilizer. Type is step-down DC-DC. Input voltage range from 12 to 30 volts, but can try up to 35. But I preferred not to risk it and check the circuit at an input voltage up to 28 volts. The adjustment range of the output voltage is from 2 to 28 volts. In my case, the maximum voltage is 22 volts because I used low voltage transistors and it was risky to raise the voltage above this value. But with an input voltage of about 30 volts, the output can easily get up to 28 volts. The adjustment range of the output current is from 60 milliamperes to 15 amperes, depending on the resistance of the current sensor and the power circuit elements. In general, the circuit can produce currents up to 20 amperes. The device isn't afraid of short circuits, simply the limitation of current will work. A little later we will talk about this in more detail. The adjustment is quite smooth, both in current and voltage. Now let's take a closer look at the circuit and principle of operation. The unit is assembled on the basis of PWM controller TL494. The output of the chip is supplemented with a driver. In fact, it is a current amplifier and is designed for correct control of power transistors. As already mentioned, FETs are used, the couple connected in parallel to increase the power. The snag is that these are P-channel transistors and many may have problems finding them, since they aren't so popular as N-channel transistors. If you have a radio shop in the city, then there will be no problems, but in my town there are only the local hucksters who didn't have P-channel FETs with the desired characteristics. And then I remembered that I have a bunch of protection boards for lithium-ion batteries. On some boards installed P-channel FETs and they are pretty good. The problem was that I developed the stabilizer board for installing transistors in the TO220 case, and here a completely different case. So what will be shown now isn't recommended for viewing by too sensitive people. Let's go! techno version, but it works and works well. And you will see at the end, transistors are AOD403. They are low voltage, only 30 volts, but they have a very low open channel resistance, and the maximum drain current is as much as 70 amperes. But the gate capacitance, at least in my transistors, is quite impressive, about 3.5 nanofarad. Taking into account the fact that there are two transistors, the chip TL494 wouldn't feel easy, but the driver on the complementary pair copes very well with the control. The circuit shows the preferred transistors. Low voltage ones aren't recommended. About the PCB, I want to draw your attention to the capacitors installed on the output. I advise you to use capacitors with low internal resistance and voltage 40 to 50. In my case, the total capacity is about 1100 microfarad. I strongly recommend the capacity from 3 to 5000 microfarad. The printed circuit board can be downloaded with the archive of the project by the link in the description. A load resistor at the output is used to quickly discharge the output capacitors. Without it, the voltmeter at the output will respond with a delay. This is due to the fact that when the output voltage decreases, capacitors need time to discharge, and the resistor will quickly discharge them. The value of this resistor needs to be recalculated if a voltage of more than 24 volts is applied to the input. The 2-watt resistor is selected for a margin of power. During the work it can heat, this is normal, and on my board resistor isn't installed. And now let's speak about its work. We have a PWM controller that generates control pulses for power transistors and a driver to control them. In the presence of a control pulse, the transistor is open and the power is supplied through the open channel and the choke to the storage capacitor. I remind you that in our case there are two transistors in parallel. Here, P-channel FETs are used, so the control signal is removed from pins 8 and 11 of the PWM chip. There are collectors of transistors of the internal output stage. Their emitters are connected to the ground. This means that the power transistors will open when the output level of the chip is low and closes if high. We must remember that the choke is an inductive load, which is characterized by the accumulation of energy and returned due to self-induction. When the transistor closes, the energy accumulated in the choke through the Schottky diode will continue to feed the load. The diode in this case will open because the voltage from the choke has reverse polarity. This process will be repeated tens of thousands of times per second, depending on the operating frequency of the PWM chip. In fact, the PWM controller always monitors the voltage on the output capacitor. Let's try to understand how voltage stabilization works. The non-inverting input to first error amplifier, pin 1, receives the output voltage of the stabilizer. It is compared with the reference voltage which is present to inverting input. If the output voltage decreases, the voltage at pin 1 will also decrease. If it is less than the reference voltage, and in our case it is about 2 volts, the PWM controller will increase the pulse duration. Consequently, transistors will be open longer time and more energy will be pumped into the choke. If the output voltage is greater than the reference voltage, the opposite will happen. The chip will reduce the duration of the control pulses. With the divider, we can forcibly change the voltage at the non-inverting input to error amplifier, thereby increasing or decreasing the output voltage of the stabilizer as a whole. For the most accurate voltage control, I use the trimming multi-turn resistor, although it can be usual. The minimum output voltage, as said earlier, is about 2 volts and given by the specified divider. If desired, you can play with the resistance to obtain acceptable values for you, but don't advise to reduce the minimum voltage below 1 volt. The choke is wound on a yellow-white ring from the group stabilization filter of the computer power supply unit. The dimensions of the ring I used are now in front of you. Because I was planning on a fairly large input current, I used 2 rings stacked together. The winding of the choke contains 20 turns, wound with 2 wire of 1.25 mm in lacquer insulation. The inductance turned out to be about 80 to 90 microhenry. It is desirable to use a diode with a reverse voltage of 100 to 200 volts. In my case, a powerful diode assembly MBR4060 with 60 volts and 40 amperes is used. Diode assembly is in the TO247 case. Inside are two diodes of 20 amperes with a common cathode. I also paralleled the anode. As a result, I received an analog of powerful 40 amperes diode. The reverse voltage is 60 volts. Not much, but it will do. In my case, Schottky diodes are preferable. I forgot to explain the operation of the current limiting system, although the principle isn't much different from the voltage stabilization function. Here we have a current shunt. In fact, it is a resistor with very low resistance. Naturally, when a load is connected to the output of a stabilizer, there will be a voltage drop across this resistor. The greater is the current consumed by the load, the greater the drop on the resistor. For the organization of the current limiting function, a second error amplifier is used in the TL494. The voltage drop across the resistor is fed to the non-inverting input of the second error amplifier. Again compared with the reference one, and then exactly the same thing happens as in the case of voltage stabilization. This resistor can regulate the output current. The circuit lacks operational amplifier to amplify the voltage from the shunt, but it works without it. Although with an operational amplifier, the current limit would be smoother and more responsive. The current shunt was first made of two parallel low-impedance resistors with a resistance of 0.05 ohm. Hence, the total resistance was 0.025 ohm. Such shunts can be found on the board of the laptop battery, but at first short circuit the shunt burnt down. Therefore, in the end I put what were at hand, two parallel connected 5-watt resistors, 0.1 ohm each. Power transistors with diode are installed on a common radiator. Since their substrates are connected, we don't need to isolate them from the radiator. It seems all was told. Now it's time to go to the tests. First, let's check how voltage stabilization works. At the output, the stabilizer set the voltage of 5 volts, as the load will be low power lamps. At the input, we will give 12 volts and gradually raise to 20 to 25 volts. The multimeter shows the voltage at the output of the stabilizer. As you can see, when the input voltage changes, the output keeps at a given limit. Next, we will check the adjustment range of the output voltage. The input is about 23 volts. The adjustment isn't quite smooth from 2 to 20 volts. You can increase the upper limit of the output voltage by selecting the specified resistor. Of course, the output voltage can't be greater than the input voltage. Let's see what the minimum value of the current can be obtained from our stabilizer. The output is loaded with an incandescent lamp. The minimum current is of about 60 milliamperes, quite good. Well, now the power tests. The power source, in this case, two series connected batteries, that is about 24 volts, is fed to the input of the stabilizer. In addition to this, parallel to the batteries is connected an auxiliary power source, because the batteries are far from the first freshness. The first multimeter shows the voltage at the output of the stabilizer, the second at the input, that is, the voltage that is on the batteries. The value of the output current I measure with a clamp meter. The oscilloscope shows voltage ripples. It's connected in parallel to the load. A scale is 5 volts division. The divider on the oscilloscope probe is disconnected. Here I will note there will be losses on power wires and connections. This should be taken into account. I also connected an additional capacitor at 2200 microfarads to the output, parallel to the ones that were already on the board. Current is 3 amperes, as allowed in nichrome heating element. The voltage drawdown at the output is about 0.2 volts. The output voltage ripple you can see for yourself. The division is 5 volts. Current is 5 amperes. Voltage drop is a half volt. Ripple, in principle, at the same level. For a current of 10 amperes, as a load will be a lamp from a film projector. But first I push it into the box so that doesn't spoil the video or burn the table. 10 ampere voltage drop somewhere 0.6 volt. Voltage ripple a little bit more. Plus all sorts of interferences of unknown origin. I will not torture device more, or will be more precise. I will do it another time when normal transistors come. Not bad. Someone will say that the ripple is too big, but here are 2 points. Firstly, the total capacity at the output is smaller than necessary. And secondly, I planned this device more like a charger. And in the charger, such pulsations are quite allowed. It isn't harmful for the battery. What about the components heating up? And how does this stabilizer hold short circuits? Well, let's begin. Here I note that the shunt is already different. Clamps that were installed initially burned immediately. However, this has already been mentioned. Of course, it is desirable to use a shunt of Constantan or manganin. They will not change the resistance as it warms up. And these resistors aren't the best option, but they will fit if there is nothing else at hand. At the input is fed 24 volts from the batteries. If the circuit doesn't work perfectly well, then everything will burn to hell, because the battery current is very big and not limited. Not bad, right? Now I set a current limit of 5 amperes and close the output of the circuit through the ammeter. Let's wait for some time and measure the heat dissipation on the power components. Notice transistors and diode without radiator. A power diode, a shunt, and the limiting resistor on the power supply of the chip are heated, but the temperature on them, given a rather impressive current of 5 amperes, is only 40 to 45 degrees Celsius. Power transistors and the choke are cold. It's good. At the end, I measure the no-load current. As we can see, at 24 volts input and about 11 volts at the output, the current consumption is only 10 milliamperes. This is a very good result. Well, let's summarize. The stabilizer isn't bad. Smooth adjustment for current and voltage, good stabilization. It holds short circuits without problems, is relatively simple and doesn't require large financial spending. If desired, you can increase the output current to 20 or more amperes. I made this stabilizer for inserting into a powerful charger. I will wait for normal transistors, then will drive a bit more, torture, so to speak, and look what will happen. Perhaps the circuit will be refined. Indicators of operating modes will be added, and protection against polarity reversal will be added too. By the way, now the circuit is afraid of reverse polarity. We will probably work on reducing the voltage ripple, although I repeat, this is not a laboratory unit, but a charger. On this, friends, video comes to an end. I really hope that you liked the video. If it's so, don't forget to rate it, and if you have additional questions, ask them in our group. The link is in the description. Also, there is a link to the project archive in the description with the circuit and the board. Now I say goodbye. Until we meet again. With you was Kasyan TV.